Over the past decade, several representations have been refined to digitally reconstruct the objects. SDF-alike representations are largely employed to describe complex surfaces. However, they are implicit, and the shape is not readily available. Point clouds are reliable representations of scans, as they continuously define points in space. Volumetric representations are used in rendering because of their efficient and discrete nature. Finally, meshes explicitly define the surfaces by means of polygons, often triangles. As such, they are the de facto standard shape representation. Let's have a look at this representation a bit further. Manipulating meshes through maps, however, is not a trivial task. Just look at the example on the left. Optimizing the vertex location of a mesh, following a gradient, shown with blue arrow, causes the mesh to fold. To avoid this issue, ad hoc rules must be defined for each problem. The underlying issue relates to the discrete and combinatorial nature of meshes, while maps assume them to be continuous. Hence, meshes are not naturally suited to be composed with maps. In this work, we propose a novel representation called neural surface. This representation is continuous, differentiable, and naturally composable with maps. Given a mesh describing our target surface, we pair it with a chart. We have now a map F, 2D, 3D. We refit this map with a neural network phi by minimizing the deviation from the surface. The weights of this neural network define the final representation, hence giving us a fixed shape. Furthermore, our neural surface will inherit all qualities of neural networks, and being continuous and differentiable. Let's now compose this neural surface with a map. Here, we compose a neural surface map phi with a neural map h by mapping the domain of phi onto a new domain. In practice, the surface is fixed, and we optimize the composition just by changing h. For example, minimizing the conformal energy, we obtain a conformal parametrization of the shape independently of the initial chart. This formulation is not limited to conformal, any differentiable measure can be optimized. Let's now have a look at the conformal energy optimized over time by looking at the texture. You can see how clearly the shapes kept fixed over time. To complicate the picture even further, we can add another neural surface. Here, psi is composed to the output of the neural map h. Now, by pulling a point from one neural surface to its domain, then push it through the neural map h, and finally over the other neural surface, we achieve the surface-to-surface map. Such a map is continuous and differentiable, allowing to minimize end-to-end measures like distortion between two surfaces, only by manipulating h. For more details and to see how this formulation is extended to a collection of shapes, please refer to the paper.